If you're wondering about the not-so-basics of limits, then let's get going. Welcome to another episode of the EduHaven course on AP Calculus. If you're ready to succeed, let's go.
Before we start, I just want to say that this is called the squeeze theorem. It's also called the sandwich theorem. So, if I refer to any of those names, they're the same thing.
This means that when you have three functions, g of x, which is less than or equal to f of x, which is less than or equal to h of x, the limits follow the same property. Then, if the limits on g of x and h of x are the same thing, that means f of x has to have the same value as well. You can think of this as like a limit sandwich. Typically, when using the sandwich theorem, we try to find an inequality that exists. For example, with cosine 1 over x, we know that the value of the function is either between -1 and 1. This is because it's a trig function. Then, if we multiply each function by x squared, we get this. However, we know that x will approach 0, so you can also multiply the edges by 0. This means that the inner function has to equal 0 as x approaches 0, because it's between 0 and 0. Let's expand upon this. For example, with this function, if we multiply by 3 over 3, we end up getting this. However, it can be simplified to 3 times the limit of sine of 3x over 3x. From this, we can see that this is just the octopus function, so the limit is 1. Multiply by 3, you get 3. This leaves us with this generalization. By a similar process, you can also get this generalization, and you can also get this generalization. These can be useful when solving for limits and you don't want to use the sandwich theorem fully. A common misconception with horizontal asymptotes is that they only look like this. However, for a function like the octopus function, the function oscillates over a certain value, 0. This can also be a horizontal asymptote. While you can use your pre-calculus horizontal asymptote knowledge of rational functions, you can also take the limit to infinity, which can be a little scary. With limits to infinity, you can't really plug in infinity. However, you can use some intuition. For example, for 1 over x, as x gets really big, the function gets really small, or approaching 0. Therefore, we can say the limit as x approaches infinity of this function is 0. Another idea is the greatest part of a function. For example, with this function, x plus 1, we know that as x approaches infinity, x gets really big. However, the plus 1 doesn't really matter in the grand scheme of things. This means that the limit as x approaches infinity does not exist, because x is infinity pretty much. This is called the end behavior model, and is typically used for polynomial functions. For a polynomial like this, the end behavior model would look like this, because this is the highest degree term of the polynomial. Now, you have to remember that this end behavior model is not equal to the function. Rather, it's a tool that you can use to find the limit as x approaches infinity or negative infinity. Similar to before, you can also take the end behavior model of a rational function by just taking the highest degree term on the top and the bottom. Then, you just cancel the terms. If an exponent remains on the top, the limit does not exist. However, if an exponent remains on the bottom, the limit is 0, which means the horizontal asymptote is 0. After canceling the x's out, and you just get a number, this is the horizontal asymptote. You kind of have to play around with end behavior models and practice with them a lot, but here's some general rule of thumb. With trig functions, at the bare bones, they only go between -1 and 1, so they're typically not the highest degree. When you have a number raised to x, like e to the x in this case, it usually has more power to the right because it increases, while on the left it approaches 0. With the absolute value of x, as it's approaching infinity, you should plug in x. However, when approaching negative infinity, you should plug in negative x and go from there. You can also use limits to find vertical asymptotes. Instead of approaching infinity, you have to see what value x has to approach so that the limit equals infinity or negative infinity. For example, with this function, you have to ask yourself, when does the function equal infinity? And the answer would be when the denominator is 0. So you have to look for an x value in which the denominator is 0, or this one. There are 3 types of discontinuities. A removable discontinuity is when there's a hole in the function. A jump discontinuity is when it's a piecewise function and the function jumps the value. Lastly, an essential discontinuity is when the limit approaches infinity or negative infinity. If any of these are present, the function is not continuous. However, if none of these are present and the function is continuous, then you can use the intermediate value theorem. The intermediate value theorem states that when a function is continuous along an interval, there exists a value, f of c, in which the value is equal to a number in between the starting and the ending point, f of a and f of b. This just means that when you have a starting and an ending point, there exists a value in the middle. This can be really useful in order to prove that a function has a certain value when you know that the starting and ending point is at certain points and the function is continuous, like this. When you have the limit of a composite function, you take the limit from the inner function first. However, you have to see which way it's approaching that value. If from above, the limit of the outer function should be taken from the right. However, if from below, the limit of the outer function should be taken from the left. And that's all for Unit 1 of the EduHaven course on AP Calculus. If you've enjoyed this episode, consider subscribing. If you want to check out another EduHaven course, click right here. Thanks for watching, and I hope you succeed.